geopend. De heer Arpan Koirala, Erasmus Mundus Master of Science in Sustainable Transportation and Electrical Power Systems, Universidad de Viedo, Asturias in Spanje, heeft aan de faculteit een proefschrift voorgelegd handelend over stochastic hosting capacity of low voltage distribution systems using polynomial chaos expansion. Stochastische onthaalcapaciteit van lage spanningsdistributienetwerken met behulp van polynomial chaos expansion. En dit tot het verkrijgen van de graad van dokter in ingenieurswetenschappen. En zal dit proefschrift nu in een openbare zitting verdedigen. Vraag aan de kandidaat heeft een uiteenzetting gegeven van ongeveer 45 minuten. Daarna zal er gelegenheid zijn tot het maken van opmerkingen en het stellen van vragen. Arpan, floor is yours for about 45 minutes. Okay, please start.
Good afternoon, good evening, everyone. Is it audible? Yeah, okay. Thank you for being here for the presentation as well as my public defense today. And as I see the title, it's about stochastic hosting capacity of low voltage distribution system using polynomial chaos. But we have a common audience here, so I'll start with the motivation first and then try to link the title with the motivation and so on. So there is no doubt at all global warming is happening. And if you see the history of our measurements, so in Belgium, the measurement started in 1892. So if you compare from the decade of 1850 to 1900, the temperature has already grown in average by 2.7 degrees Celsius. And in worldwide level, the rise is between 1.1 degrees Celsius and 1.12 degrees Celsius. But if you see from recent few years back, so this is the timeline only of 4 years. I started my PhD around 2018. And if you see, I always used to hear the complaint of Belgian people saying it always rain. And last summer, it was the first time I hear that Belgian people were really saying, we need rain, we need rain. So the things are changing very fast in the last 5 years. And the recent one, this new year was like 16 degrees Celsius, which was like first in its record, like 16 degree in December was nothing we have seen in country like continental Europe or something like that. So global warming is happening. And the impact is not only these few heat waves or some floods we are seeing or rain in some random places where there are no rain, but the sea level is rising. There is also the ozone layer, which is getting bigger and ozone hole, which is getting bigger and bigger. If you remember, there was a flood in Belgium for the first time. I think it was for the first time there was a flood in Belgium. And in all Western Europe. And what is the culprit for this? Generally, it is considered global greenhouse gases emission is the culprit or the causes for this. And if you see there, carbon dioxide is the major contributor. And if you see the index of how the carbon dioxide emission is growing from the decades from 1850 or 1900 to now, it's already tenfold more carbon dioxide we're emitting in total, which is causing this global warming. Saying so, okay, one of the solution might be, we are scientists, we saw some solution, and energy transition might be a solution, it might help. And basically it means shifting from more fossil fuel-based system to more and more renewable energy, like wind and solar. And how are we going to achieve this? And in EU level, if you see, there are lots of new policies coming on, saying, for example, there should be a greenhouse gas cut by 40% by 2030, or reduce the emission from transport by 13%, or in Belgian level, if you see, it's like Belgium targets to generate 18% from renewable energy by 2030, and also phase out the car with combustion engine by 2029. So are you already seeing the impact of this policy? If you see, the number of electric vehicles are increasing day by day, and so is the new PV being installed, or also the heat pumps. So in 2022 only in EU, there were already more than 41 gigawatt of new PVs. And by 2030, there will be more than 510 gigawatt of PV, of which 70% will be connected in low voltage distribution system, which is also the part we will be discussing more. And in Belgium, there will be almost 5 gigawatt of solar PV by 2030. So now we come for the power system. If you see this system, it's a more traditional system where there were big generation plants from coal power plants or nuclear power plant or other type of thermal power plant. They were being transmitted using transmission network to the consumers or the distribution load, which is usually in low voltage in 230 volts or 400 volts. And so the distribution system designed for this traditional power system is more for one-way power flow from this big generator to the house of the consumer. But as I said, energy transition is happening. There are lots and lots of PV being in the rooftop of our houses, and a lot of people charging electric vehicles. So the system designed for this traditional one-way power flow might not be as simple as before, because let's say one example, it's summer, everyone is in holiday, but your rooftop is still producing some electricity. But there is minimum load in your house, so a lot of energy has to be sent back to the main grid from the low voltage distribution network. While if you consider a winter like this, nobody is going on holiday, everyone goes back from office at 6 o'clock, try to plug in their electric vehicles, try to plug in their heaters and whatever devices they have. And a big amount of electricity is withdrawn from the grid. So if I was the guy sitting behind this screen in this traditional grid, I would be having my sip of coffee all the time, just hanging around. But with the system, it will not be I'll be sweating around, trying to figure out how to supply this varying load, which varies from time and again. So in our work, we try to support these people who are operating the which are operating the grid. So we call ourselves decision support groups. So basically, we are not staying behind that screen, but we are trying to support the people who are staying behind that screen in our work or in this work. So how do as I said, it's getting problematic because of these new resources, but then it has to be done something, right? And the thing we have to do is more and more infrastructure. Maybe that might be one solution, and EU envision that there will be at least 29 billion of investment required to upgrade the grid for this new installation, new PV or this device supporting energy transition, while the distribution system operators, the group of distribution system operator thinks that it will be more than 4 billion of investment. And in Belgium, or in Flanders, Fluvius has already brought forward its investment plan for 2023 to 2032, which is almost like 4 billion, and 75% will go for the low voltage distribution network. So low voltage distribution system will be more major constraint in this energy transition and requires a hefty investment. However, the existing planning approach are more and more based on fit and forget approach, which is more passive, deterministic, and we design for the worst case. It means that, okay, we say like the maximum voltage or minimum voltage can go this much, or their load can go in a worst case scenario this much, and we design for that. And it might lead to some over-designing problem. However, these network congestion are very rare events, so it can occur for a few hours or few slots of only on the few time over the day. And the low voltage distribution network, they can be congested for a while, so it's not a robust problem that we have to be within the limit for all the time, but there is always a little bit margin. Always we can say, like, for 15 minutes or for 1 hour, we can go 110% of the rating or something like that. And moreover, this PV generation and consumer load along the day, they are stochastic. So if you see the irradiance profile here, so it's not same over the day, and from one day to another, it's also vary. Same is our house load. So we don't always cook at 7 o'clock in the evening, but someday we just go to the restaurant to eat and so on. So it's varying every day. So in this context, we need more stochastic planning tools which consider these stochastic limits or stochastic variables rather than doing more deterministic and worst case design. This will finally reduce or eventually reduce the cost of energy transition, or we can transfer it to future by reducing the need of more extra additional infrastructure. So in this thesis, we deal with one of such problem, like how much PV it can be our system can accommodate, or the low voltage distribution network can accommodate. So coming to my PhD now, this was done in a global scope of Project Prequilab. It was again energy transition funded. It already shows like people are investing a lot in also in research and development. And what we found was the actual PV potential was the minima of rooftop availability or the grid availability or market and consumer preference. So it might be just your grid is very sufficient, but you don't have enough space in the roof, or even consumer are not willing to buy the PV, or there is rooftop availability. Their consumer are very interested to buy PV, but there is no enough capacity of the grid. And the work we focus in this is mostly on the grid hosting capacity, where we try to find what is the limitation of the grid and what can be done for. So this thesis has three main objectives. As I said, the first one will be mostly about understanding the hosting capacity, like how much PV can be absorbed in our grid, and trying to determine the hosting capacity of our grid. And the second one will be trying to find out new calculation method for this stochastic hosting capacity, and we'll deal why the new methods are required later. And finally, we also try to find out the hosting capacity of the big service area or a big region. In terms of the chapter, so the first two chapters of my thesis are more about the introduction and the basics of the low voltage distribution system modeling and probabilistic approaches, while in chapter 3 we try to deal mostly with the understanding the hosting capacity, how they are calculated, and so on. In chapter 4 is more about the calculation method. Chapter 5 and 6 we propose new hosting capacity calculation based on a more new calculation tool we propose in chapter 4. And 7 is more about representative feeders to scale the hosting capacity, and we conclude the thesis. These are the chapter in this, and I don't want you to worry about this. I'll come back about this later when I come to the chapter, but yeah. So let's start with the hosting capacity. As I said, hosting capacity is the amount of new generation or consumption that can be accommodated on the given feeder without enacting the system operation, without any impact in the system operations. So this is the low voltage distribution grid. These are the houses, and how much PV can this house can easily accommodate without hampering the overall system operation. So we start with benchmarking of the PV hosting capacity, and before when we started this topic, the first thing was we said like, okay, we try to find the best method available in the literature, we use that, and then try to find the hosting capacity. But then we realized, okay, there are many different definitions of hosting capacity in literature. They use all different test feeders, different limits, different assumptions, and choosing one method was very difficult. However, we have this network data, which I did my master's thesis on, and we thought like, why not to implement all those existing methods in this network with almost 8,000 consumers, representing a small suburban area with almost 160 low voltage distribution feeders and 30 transformers, and try to do some sensitivity analysis of these limits, as well as try to see what different assumption was taking place, role of different assumptions. So what we conclude was most of the method was this iterative methods, where we take multiple feeders and start from feeder 1. We try to do some initial PV deployment scenario. Then we do some probabilistic power flow or power flow. We try to see if the grid constraints are violated or not. If not, we try to increase the amount of PV in that grid. Try to see if it is violated or not. Finally, if there is violation, we stop there, and that is the hosting capacity, or the previous scenario is the hosting capacity for that particular grid. We continue for all the feeders, and then the sum of the individual hosting capacity is considered as the hosting capacity of the whole network. We implemented this for almost 11 stochastic method and 3 deterministic methods. This deterministic method were more standard method we framed, but the stochastic method were the exact method in different papers by different authors. And as you see already, so the middle one in the gray is the reference method, and all other methods were giving hosting capacity all over this space. That means if somebody is saying, okay, the hosting capacity of this network is 15 kilowatt peak or something like that, we always have to look what is the assumption taken behind, or what are the limits they are taking, because it's not very easy to understand. However, we say that stochastic hosting capacity was better and give more information than the deterministic one, for sure. This was also the conclusion of other authors, and we also see the same. Then the other thing we did was we took the reference method and we tried to see how sensitive is the method to the stochastic constant and also the voltage limits. And as you see, the spread was again used. So you have the same assumption on the input, but even if you are changing the stochastic constant or changing the voltage constant, the change is quite huge, and the range, see, it can be anywhere. So anyway, with this, we conclude that stochastic hosting capacity is a multidimensional stochastic planning problem because of this input uncertainties, as well as the uncertainty, the chance constant we can impose on the grid limits, while the iterative PV deployment with Monte Carlo makes the stochastic hosting capacity a computationally very complex problem, and we then explore some better uncertainty quantification tool so that we could solve this problem more faster and more accurate. So as I now shift to the uncertainty quantification, I think it's a good way to show what uncertainty quantification means, or how does it actually works. So always the first step is, don't get confused with the one in the right, it's one in the middle. So the first step is you will need to understand your system first. You understand your model or system or whatever you have. So in our case, it was more power flow equations and network informations. Once we have that, then we try to see what are the uncertain input for them. And in this case, maybe load or irradiance was the uncertain symbol, uncertain sources, and try to quantify them. And finally, we need to propagate those uncertainty sources or the quantified one through this our system model to get the output. And the output is generally in the form of PDF, in the mean of the value, or in the terms of, in our case, it was probability of undervoltage, which is again mostly lies in the tail region if you see there, and it makes it more complex problem to solve because computing a mean would be easier, of course, than computing what is the probability of voltage getting violated. So we try to do different uncertainty quantification tool. As I said, Monte Carlo is a very traditional one. Everyone uses it because it's simple. What you do is you just sample the distribution space, then try to pass it through our model equation, and we get the solution or the output. And it's simple and easy to implement. However, it is computationally intractable whenever the model are expensive. But then we have some new methods like polynomial chaos. Instead of trying to solve for all this realization, which only try to take some few nodes and try to replicate the behavior of model in that node and try to then sample bigger space and try to use get the output. It replaces the computationally expensive model with more polynomial surrogate, however, requires some pre-calculation and complex math compared to the Monte Carlo methods. So we are talking more about polynomial chaos because it occupies almost 50% of or 30% of my PhD title. So it's a method for representing the stochastic variable in terms of linear sum of polynomial functions in stochastic of the stochastic variables, and the polynomial chosen are usually of a special type. They are called orthogonal polynomials. Many of us in this room might be aware about the vector geometry, where we can represent any point P in terms of the linear sum of ijk, or maybe go complex. Most of us are electrical engineers, so if you have heard about Fourier transform, where we can write any periodic signal in terms of sine and cosine with their coefficients. Here we write in terms of orthogonal polynomials in polynomial chaos. So basically you have y is a stochastic variable. It can be expressed as the sum of orthogonal basis polynomial with some weight. And the polynomial looks something like that below the phi naught, phi 1, phi 2, something like that for the normal distribution with mu1 as a mean and sigma as a standard deviation. So I know this is not a very sufficient explanation, but yeah, if you need more information, we can always discuss, or we can have a longer meeting. But what you need to know, maybe to understand, follow the remaining slides, is that there are two types of polynomial chaos. This one is non-intrusive polynomial chaos, where a surrogate model is formed of the power flow equation. So what we do here is we take few points, which is called testing vector, and try to do the power flow evaluation in that point and make a surrogate model G bar. And that the remaining part is like Monte Carlo simulation. So you make a lot of uncertainty realization now pass through the surrogate model instead of the power flow evaluation and get the quantity of the interest. But there is another variant of it called intrusive polynomial chaos, where instead of trying to make a surrogate of the model, what we try to do is we try to intrude the system equation. So we have a system we have physics defining the system. We try to include those differential equations or whatever equation we have, use Galerkin projection, try to, we have our system equation. We try to represent the input with orthogonal polynomials. So we have our input uncertainty. We represent using orthogonal polynomials. Then we try to project it through the system equations. So while doing so, one advantage is we can completely transform the equation in more coefficient basis. So instead of carrying out whole polynomials, we just take the coefficients and we try to transform the coefficient from the input to the output realization. So as I said, the first one doesn't require any understanding of the system. We just treat the system as a black box, and it's good if you are doing just probabilistic power flow. And the second one, we need to understand the system equations, and it's very beneficial if you want to do some optimization in the system. So coming back to these iterative methods again, so the first thing we want to try in chapter 4 to increase the hosting capacity was try to do this probabilistic power flow, try to make it more faster or more efficient. But in literature, there was different uncertainty quantification techniques, and it was very difficult to understand which one is the best for calculating PV hosting capacity. So what we did was we did this. The methods highlighted in blue, Monte Carlo, quasi-Monte Carlo, and non-intrusive PV, we compare them and try to evaluate which is the best one. So in comparison, it was seen that degree 2 polynomial chaos, so I'm talking now about the non-intrusive one, and if you see here, it had the accuracy almost equivalent to the Monte Carlo for same number of samples, while the computation time for most of the case, it was almost 10 times less than the Monte Carlo samples. Monte Carlo simulations with the accuracy almost equivalent like a Monte Carlo. And we also did it in this bigger Spanish network where we tried to see the probability of congestion, what is the error of quasi-Monte Carlo or Monte Carlo in comparison to the general polynomial chaos, and it was seen that polynomial chaos outweigh Monte Carlo and QMC or quasi-Monte Carlo when calculating the probability of congestion. Yeah. Then this was first attempt of trying to reduce the computation time of that iterative method. But in second attempt in chapter 5 and 6, we try to see whether we can maybe replace this iterative PV deployment where we are iterating every time with increased scenario with some better method. Now we have better probabilistic power flow, so I think that was an immediate next step we had to take. However, if you see the reference method, so this is the representation of reference method. So what we do was we sample all the uncertainties together and try to increase the amount of PV in every step and try to find if there is violation or not. However, this was very counterintuitive sometimes because it was very difficult to understand what was the impact of different type of uncertainty sources or it was, as I said, very difficult in another way because there were some variables which was discrete and some other uncertain variables which was continuous. So what we did was we tried to propose a new methods where we try to decouple these uncertainties in terms of operationals and planning, where, for example, the PV type or PV size and PV location, they are more planning problem because once we put the PV is fixed there, but the consumer load or PV generation, they are more variables every day. So it varies from today to tomorrow, but the PV size once installed doesn't change. So we try to decouple these two different problems or different uncertainties and try to find out the probability of congestions for each planning scenarios, and the decoupled hosting capacity is calculated as the best planning scenarios within the defined limits. One immediate advantage was that we could apply different quantification techniques for different type of uncertainty with this. So all those planning uncertainties which are more discrete, we use Monte Carlo methods to form many scenarios. And for each scenario, you could use polynomial chaos instead of Monte Carlo to compute the probability of congestion. And the one with the best scenarios under the limit was considered as the hosting capacity. But the bigger advantage was on trying to see the impact of different operational scenarios. For example, in this case, the first one is without any intervention. So there is a PV, there is no intervention like allowing of curtailment or so. And in second, we said like, okay, 75% of the time curtailment is not allowed, but 25% of the time there is allowance of some voltage can be violated or the load can be curtailed. And if you see on the right hand side, the amount of PV that can be hosted increases drastically and in order of 3. So this type of study was very difficult when you had operational and planning things sampled all together. However, though it was a very interesting way to calculate the hosting capacity, it was still a brute force approach because we were trying to do a lot of planning scenarios, trying to see probability of congestion in every scenario. So it was a brute force approach, and it was taking quite a long time to solve, or we need a lot of we're just saying like all the consumer have equal PV or something like that. So here we use the second variant of the polynomial chaos, which is non-intrusive, the intrusive one, where we know the system equation and we try to intrude the system equation from the known uncertainty to define it as a optimization problem. So through PC, stochastic OPF was reformulated as a deterministic OPF over a set of network replicates. So if you remember in Fourier transform, you can play around the coefficient and try to change from time domain to frequency domain. Here we change from the actual uncertainty domain to the orthogonal polynomial domain or the coefficient domain, basically. And for certain distribution like normal, beta, and gamma, we had the exact representation with a polynomial degree of 2, which made our work easy. And it was the amount of network replicate we required. So that means the number of coefficient required was very few compared to the Monte Carlo for the same level of accuracy. So we did a simple test with a very simple feeder with only 7 consumers and possibility of PV size between 0 to 15 kilowatt peak. And without scenario reduction, it was already more than 68 million scenarios. We tried to reduce the scenarios a bit, and still it was 2 million scenarios. And if you see the computation time with the reduced scenarios, it was already 3 days. And with this new framework, it was already in few seconds or fractions of seconds. And you can see the accuracy, okay, it's almost, I think this one is better, but I am showing this another histogram where the blue one were the feasible scenarios or the scenarios of the PV, which are feasible using our scenario-based method, and the red one were the infeasible scenarios. And if you see the black line in the middle, there's the solution from this approach. So basically, it gives you the best possible solution or the best possible if your distribution service operators has a right to put that 15 kilowatt peak wherever they want. But however, we also made it in such a way we can tune those limits according to rooftop area or according to the consumer preference or so on. So it was just basically changing the limit of the variables in the optimization problem. We also did again for the same Spanish network. We tried to see for how does it look for in a bigger system, and it was seen that this stochastic OPF was better or the deterministic one, because the deterministic one was, I think, underestimating in an average 20% of time, 20% of underestimation of the hosting capacity. And yeah, no need to say that I think I've repeated already. So using this method, we are not relaxing anything in our power flow equation. So that we use the exact power flow equation. We didn't linearize anything or try to relax anything. And we also didn't need any samplings. And it's computation time reduced to a few seconds. And in real networks, it was estimating like 20% underestimation of hosting costs. Now we come to the chapter 7. Okay, we said like, okay, initial this PV deployment scenarios is replaced by one such solution, but still there are like thousands of feeders. For example, this dot you see there, I couldn't even mark a circle in the map. So it was that small area and that already had 160 feeders. What if you need to calculate the hosting capacity of whole country? It will be like the number of feeders will be in million, if not in hundred of thousands. And solving that even with this improved method might not be always fruitful. And if you have to do like number of scenarios, then it's more problematic. And moreover, if you want to do scenario check for 2050 or so on, and then we also don't know how the feeder look like in the future. So what we say is we propose some clustering scheme so that we could use some most relevant features for and get the representative feeders to scale the PV hosting capacity and to act with a mind on comparing like, okay, how accuracy and number of representative feeders place can be affected. So for this, we use some known features of these features like number of consumers or yearly consumption, yearly reactive power, total conductor length, main path, and so on. And if you see in the graph, so the one in the blue is using all features. So what you realize, like, okay, clustering using all features might not be giving us a very best representative feeders. However, we try to select the better features. And with a better feature selection, the amount of feeder required or the representative feeder required was reduced to the 3% instead of 35% while using all features. And we realized like the number of consumer in a feeder or the total conductor length and the average length to the consumer were like main features which are influencing the hosting capacity or the scaling of the hosting capacity. And 3% of the feeders resulted in the scale hosting capacity with an error of 20%. But as I said, if you need less error, then we can increase the number of representative feeders and vice versa. So I now want to summarize all those contributions. And so what we realized was the stochastic hosting capacity was required in low voltage distribution network, but they were being computed iteratively using power flow equation and Monte Carlo simulation for each feeder. However, this computational burden will force us to neglect some of the sources of uncertainties or use less Monte Carlo samples or approximate the power flow equations or also sample the planning and operational uncertainties together to name some. So what we did was we tried to introduce this new probabilistic power flow based on non-intrusive GPC to reduce the computational time of Monte Carlo simulation. We also tried to bring this intrusive GPC based or polynomial chaos based stochastic OPF that replaced the iterative PV deployment to get a single source solution of decoupled PV hosting capacity. And finally, we also showed that properly selected representative feeders replaces computing this stochastic hosting capacity for all low voltage distribution feeder. And this was the chapter I was not explaining in the before, so now I think it makes sense what I've done and how it is spread out in the different chapters. So time to conclusion. So what we realized was hosting capacity was more multidimensional stochastic problem, as the input are more stochastic and the grid limits are probabilistic. The planning uncertainties and the operational uncertainties, they need to be decoupled to have a better planning of low voltage systems, to understand what are the impact of different operational criteria or different planning criteria. We can solve this hosting capacity as a one-set problem using intrusive polynomial chaos. And using this new SOP app, the hosting capacity of same network was increased, or was 20% more compared to the traditional deterministic OPI. And finally, 3% of the feeder would be represented to scale the hosting capacity to the large service area. And in new calculation method, what we see was non-intrusive polynomial chaos reduced the computation time of Monte Carlo simulations while performing probabilistic power flow. And the intrusive polynomial chaos can be used to have one-set solution, bringing computation time scenario-based stochastic methods from days to second. And this can be also used in other applications. We have an open source toolbox which can be used for other applications, or we are already using for other applications, to not only stochastic hosting capacity. And we also identified some future lines of work. For example, the LVDS power quality, they are limited by the measurement device in low voltage distribution system. We don't have a per second measurement in low voltage distribution system. Most of the measurement are by smart meter, which is 15-minute average. And some of the power quality are like based on 10-minute average or instantaneous or something like that. So there should be some changes in this practical standards. The stochastic OPF still can be extended for more time-dependent loads like battery storage and heat pump. And so for that, we still need to work on making stochastic OPF faster so that we could introduce more and more uncertainties in the system or in our computation framework. And finally, the open LVDS data, making data public and usable will increase the transparency in investment planning. And I think we should try to convince a lot of DSOs just to make the data public so that we can work on or make more transparent decision on this. So without waiting more, I think I want to say thank you for your attention, and now it's interesting time for questions.
Thank you very much for the nice presentation. Exactly 45 minutes, I think. It's really well planned. And let me now introduce the members of the examination committee to you. I'll do that in the order they will ask questions and make remarks later on. We'll start with Professor Lina Roald from the Department of Electrical and Computer Engineering of the University of Wisconsin-Madison in the United States. And we see you on the screen already. Followed by Professor Francois Vallee of the Electrical Power Engineering Unit, University of Mons. Professor Thérèse Steenberghen of the Faculty of Science, Department of Earth and Environmental Sciences will